Okay, so we'll be starting again in a couple of minutes. So hopefully everyone's had a chance to grab something to drink or eat and get ready. Oh, actually, quick question for Rosa.
Yes.
I'm putting out a quick ad on Twitter for each session. Do you have a Twitter that I should link to?
I do. I usually don't
Okay.
use it, but
Okay, well, it's up to you, but if you can, if you Slack me the name, I'll put it in.
all right.
Thanks.
Thank you.
I remember when we started this last year, everyone was still figuring out, how Zoom meetings go and so on. So I think we had a lot more technical issues. I'm glad that it's gone pretty smoothly today.
Yeah, this is my first time using Zoom. So seems fine.
Oh, wow. Okay. Well, even better. Yeah. Really? First time?
Yeah, I mean, I work in IT. I refused to install it on my machine for a long time because there were, there was a lot of fuss about security issues. We use Google Meet and GoToMeeting and various other things. Sorry.
Zoom's also just gotten a lot better and more secure.
Yeah.
Over the past year.
So is Google Meet, actually. I logged in recently and they made it so that the hang up button isn't close to all the other buttons.
Yes, that was a constant pain point. Yep.
In my other research interests on browsers, people sometimes ask, isn't design just like a bunch of artistic nonsense? Do we really need to look at it from a formal verification lens? And I think this is a great example of where that's not the case. Yeah, okay, so I think we are ready to start. As I mentioned, we'll be reducing the error in the start times of each session as much as possible. So our next session is going to be started off by Mark Dickinson. So Mark Dickinson is a man who wears many hats. He has a PhD in mathematics and was formerly an algebraic number theorist. Now his day job is as a director of software architecture at Enthought, which is a sort of numerics and scientific computing kind of consultancy. But today he is speaking with his third hat on, which is as a Python core developer. So Mark will be talking about numerics in Python and the Python standard library. So please, Mark, take it away.
All right, great. Everybody can hear me okay? Yeah, so first of all, thank you very much for inviting me to speak. My initial contact with Pavel was a result of me being rude about Herbie and Stack Overflow. So I'm not quite sure what lesson to draw from that, but anyway, I'm here, so thank you. Okay, so yeah, as Pavel said, I'm speaking with my Python core developer hat on. So I've been a core developer for maybe the last 15 years. People may or may not be familiar with Python, so I've got some quick introductions here. What is Python? 30-year-old general purpose programming language. It's used a lot in data science, and it's a foundation of what we do at Enthought. It's got a reference implementation called CPython, not surprisingly written in C. And back in the bad old days, so CPython kind of just inherited all its floating point behavior from C. That was the end of the story. And then over time, it's got a little bit more complicated. And this talk, I have to apologize, this talk is a bit of a rant. So I want to try and soften the rant a little bit by saying, IEEE 754, nobody's going to be surprised. the standardization of floating point has been a boon to Python, to C, to NumPy, to the scientific community at large, right? It's hugely beneficial. And I could easily go on for 10 minutes enumerating the various benefits, but that's not what this talk is about. So as a rule, it's been great. I want to focus on an exception to this rule. So we're going to drill down just to one particular ranty topic within this. Okay. And yeah, okay, brief history of Python and floating point. I'm not going to read out everything on this slide, but yeah, we spent 30 years. I've personally spent 15 years working with Python and floating point. We've seen all sorts of things, bad compilers, silly optimizations, poor C math library optimizations, poor math library implementations. Some of them are still around. If you look at the Windows FMA implementation, there are still issues there. Yeah, crazy floating point formats. Okay, we don't see cray or vax anymore, but you just still see IBM hexadecimal floating point around. Double sometimes raises its ugly head. So I personally had a lot of involvement with the development of the decimal package, which is arbitrary precision decimal floating point. And yeah, and so on and so on. Okay, user education, of course, is a big one. So lots of issues. We've dealt with them all, sort of run-of-the-mill things we expect. But there was one particular aspect that continues to cause issues, and it keeps on popping up, and we keep on working it down, and we just don't know how to fix this. And so in this talk, maybe I'm not really asking for questions, I'm asking for answers from the people who are here. So, okay, some Python background. Okay, so Python, general purpose programming language, it knows how to compare things for equality. Okay, no big surprise. There's an operator. Typically you compare two numbers, it's comparing by value, as you'd expect. Compare containers, it's going to compare by structural equality. Compare two lists, it's going to go along comparing the elements of the list. Are they all the same? And by default, you get an object identity check if you write your own type. So, okay, that's fine. You look at equality in floats, and you can dig into the Python source, of course, all open source. And eventually you find out that when you compare two floats in Python, eventually you end up somewhere down at an actual comparison of two C doubles. So Python's equality eventually just wraps C's equality. And so because Python makes no guarantees about floating point, about which floating point system it's going to use, it just picks up whatever the C double is using. But in the last 20 years, I have not seen Python ever meet any floating point format other than IEEE 754 or some variant on IEEE 754. Yeah, we're not hitting posits and B floats yet. Cray and VAX and other things are ancient history. So yeah, IEEE 754 is king, and so we end up picking up the IEEE 754 rules. Compared to numbers, we're comparing those two numeric literals are different, but they're both converted to the same floating point number. 0, -0 compare equal as dictated by the standard. Nan compares not equal to nan, again as dictated by the standard. Okay, so that's equality in floats. Okay, great. Equality in containers. So I want to talk about containers. We're using lists here, but of course Python has sets, dictionaries, other containers. So I've got a list in Python. They can be heterogeneous, different types in there. And here what I'm doing is I've created this list. It's got a float in it. It's got an integer in it, different type. It's got an embedded list. And I'm asking, is 3.15 in this list? I get the answer true. Yeah, it's the first element. Is 42 in the list? No, it isn't. It's 47.0 in the list. This one's a little bit interesting. 47, the integer is in the list. I'm asking, is the 47.0 float in the list? I get the answer true, because everything is based on equality, on value. And that's a design choice, and you can argue about whether it's good or bad, but it goes back 30 years, and it's worked out pretty well over those 30 years. So it keeps the language simple. It's part of what Python is. But here's the point of this talk. So now we have three mutually contradictory principles. Here are three things we would want to be true in Python. But logically, you can't have all these three things. So, okay, so first of all, if I have a container in Python, I put two things in it, and then I ask, is one of the things in it in that container? I would expect to get the answer yes. Right? If I put a bunch of things in the container and then ask, is one of the things I put in, and get the answer false, I'm going to be very surprised. So I have a list containing X and Y, and I ask, is X in it? I should get the answer true. Otherwise, code gets harder to reason about. And we're not just talking about humans reasoning. We're talking about static analysis tools, which are increasingly part of the developing world, sorry, the development world. So that's the first principle. Second principle, when I ask are two floats equal, I should be following IEEE 754 rules. Else we're going to get hundreds of bug reports to the bug tracker saying, Java does it this way. Why doesn't Python do it this way? All other languages I've tested do it this way. Why doesn't Python do it this way? So there's this huge value in being able to transfer numeric algorithms from language to language and having them operate pretty much the same. So we want to be following IEEE 754 rules. And then the third one, we want containment checks to be based on equality. Again, this is a sort of simplicity design choice for Python. But now you've got a problem. These two things are mutually contradictory. I put a nan into a list. I ask, is that nan in a list? Python's supposed to just go through asking, is this equal to the nan? Is this equal to the nan? Is this equal to the nan? It gets false every time. So what should it give? One of these things has to break. Okay. So, right, spoiler, it gives true. There is a sneaky solution. So Python fumbles this under the hood. It says, well, actually, when you ask it, is something in the list, we're not going to use equality. We're going to check for identity too. Problem solved, right? Suddenly all the user expectations are satisfied. We've fudged things for nan, for everything else. Identity implies equality, and so nothing changes. Nobody notices anything funny going on. So problem solved. Not really. All we've done is we pushed this problem down deeper, and now the surprises emerged a little bit later, but they're still surprises. And yeah, we've done something deeply, horribly wrong here. Now, object identity is involved in these containment checks in a surprising way. That should never happen. Right. So you ask, is meth.nan in the list containing meth.nan? You get true. You ask, is float of nan in float of nan? You get false. And this looks insane. And now you have to know details that you shouldn't have to know. You have to know that float nan creates a new nan each time. It just happens to. We implemented it that way. It didn't have to be that way. It could be returning the same one each time. And then we would have got true in the second thing. So, you know, it leaks implementation details to the user that the user shouldn't have to care about. So this is a bad solution, it seems. And yeah, the bug reports keep on coming. So this is the one that broke me. This is the Python bug report that finally broke me. You create an array of 1 million elements. That's not huge, right? You pick up just a 1,000 by 1,000 image that's got 1 million elements in it. So it's a pretty small array by scientific computing standards of nans. And I just want to count how many elements there are of different types. You know, think about a masked image or something. I can invent use cases for this. And you get a line of code which runs for hours, if not days. And the reason is every nan has a different identity, but they all have the same hash value. So it's details again. But the root of this was this dependence on identity. And so it goes back to that. Almost done with the rant, but yeah, I mean, this is it. So special cases aren't special enough to break the rules. This is a quotation from Tim Peters, who's one of the demigods of Python. The cost of this decision to make nans irreflexive, I think, is measurable. You know, there are philosophical questions about should nan be equal to nan and long screeds on the internet, but there's a real practical cost to this. And it's not just Python. You look at a lot of modern languages out there. And you look at the way that Rust handles this. Rust has an equals trait, but it doesn't work for floats. So they have a partial equal and a partial OR that were invented just for floats. So there is a real problem here. And what I want to know from you people is, how do we solve this? Yeah, we've tried bending this any number of ways in Python land. There just isn't a solution. So what do we do? So Guido is Guido van Rossum. He's the creator of Python. Famously, he has a time machine. There's even a GitHub repository for it. So maybe we borrow that, we go back to pre-1985 and we talk to the IEEE 754 committee and say, hey, look, this might look like a good decision right now, but let's go 30 years into the future and see what the impact of this is. Maybe we change things in Python back 30 years ago. Maybe we change things in Python now and then we break everything, not a good option. Lots of other technical solutions we've considered and none of them really work. So I'm kind of at the bottom one here. So live with this compromise, but yeah, I don't want to be looking back. I don't want to say what went wrong. I want to be figuring out what should we learn from this? What can we do from the future? What about new standards? What about new languages? I think for Python, it's too late. But is there something we can learn here? Is there something we can do better? So that is pretty much it. That's my 10 minutes. Yeah, a few random links. So Bertrand Meyer has a really interesting blog post, but again, it's more philosophical than practical. There's an answer from Steve Cannon of the IEEE 754 committee on Stack Overflow, a couple of other links. But yeah, questions or even better, answers.
Thanks very much for the great talk. That was super interesting. I love seeing these examples, and it was really nice how you use those to sort of draw a boundary around the design space and what the challenges are. We do have a couple of questions here in the chat, although I think I will invoke moderator privilege to ask the first one. In some sense, I think some of these examples suggest that, or I don't know, I guess this is also a question. I know you don't want questions answered with questions, but what about constructive reals? And that often gets sort of an eye roll, but it's the closest analogy that we have. In Python, things generally aren't bit vectors, right? We use big ints everywhere in Python because that matches the Python aesthetic. It gives the user more consistent experience where the grade school math they learn works in the language. What if we could do constructive reals and just, everything you have to say, well, I want the answer within this many decimal digits of accuracy. And then you get the laws, right? Then the programming experience for people is similar. Now, I think maybe what's tricky is that this starts to cleave the Python communities. There's people doing high performance, relatively high performance data stuff. They're never going to use the constructive reals. They want the float flops, right? But there's a bunch of Python users that don't care about that, and they want simplicity and predictability and these laws like you gave for the container. So have people discussed that, like, having big real where you give accuracy budgets for everything as an analogy to big ant?
Yeah, no, that has not come up. That's a really interesting set of thoughts. I think for Python's sort of too much practical. It's too much of a practical language for this, but it does make me wonder how on earth you do things like this in formal verification languages like Lean or like Agda. There's some really interesting things to think about there. So the short answer is no, this hasn't come up, but I will think about it. Thank you.
Bill, did you have a question?
I just wanted to say, as a person who builds math libraries in Python and knows a lot about Python, this was probably the most entertaining sequence of bugs I have seen in several years. So thank you for presenting it. I don't know if I should feel bad, but I was deeply, deeply entertained. And I do think that your comment that NAND being irreflexive, the equality of NAND being irreflexive has caused measurable damage in the IEEE standard. I think I agree with that on a personal level. And I think that looking forward at my own math libraries that I build, I will put more thought into this. And I don't know what the answer is for Python. I think you're absolutely right. I think that that ship has sailed, it's dead. We will be paying this cost forever. But maybe at least for other things that we build on top of it, we can do better in the future. And not have NAND compare unequal to NAND, and just silently suffer whenever you do something with a container or a hash, and then the world explodes for absolutely no observable, explainable reason that no user should ever have to care about. So yeah, I don't know, but I think there should be more exceptions or something, less just silently doing weird stuff that doesn't make any sense at all. So yeah,
absolutely. So, and there are some other questions in the question thread as well. Yeah. I think we have some good discussion on that. Yeah. But I think in the interest of time, we will go ahead and keep progressing. Thanks again for the great talk. And I'll hand it back over to Pavel.
Yeah, excellent talk. Yeah, really, really fun set of problems, and probably no one knew these were coming, but you just locked yourself into these. Okay, so we're gonna move on to the next talk. So our next talk is from Laura Titolo. She's a senior research scientist at NASA Langley. She received her PhD in computer science from the University of Udine in Italy. And a lot of her focus today is on verification and improving reliability, especially for aerospace. So easy to understand why reliability is so important there. So please, go ahead.
Hi, do you see my screen?
Yeah, we see your screen. The slides are changing sizes sometimes, but hopefully that they seem to go back to the right size.
Let me try again because Okay, yesterday it worked and now it doesn't. So bear with me 1 second.
Yep, yep.
Do you see something now? Do you see my screen or no?
No, you're not sharing right now.
Okay.
Okay, we can see your screen. We see the
Yeah, you can, but I
PDF
cannot. Do
you
you know how can I see my slides in here?
Oh no.
Yeah.
It was
I don't
actually
know.
okay before. It just when you switch slides, it zoom in and zoom back out. But we could see.
Yeah, but the problem is that I see you or Pavel, but I cannot see my slides.
Oh.
I have no idea. I never had. Someone knows that how to solve this.
If it's a laptop, then if you close your laptop lid, maybe it'll switch to a single monitor mode. That's what I did once.
Yeah, I have a single monitor now.
Yeah, if you send me the slides, we can do the thing where I'll present them and you tell me when to click.
Aww.
Yeah, it's not great.
I'm so sorry.
Laura, one last thing to check. Are there 2 windows? Sometimes this happens to me where I have 2 Zoom windows and one is showing my desktop and the other is showing the participants.
No, I have just one.
If you click on the view button at the top, you can select your view. So there is an option to swap video and shared screen and various things. So you may want to check one of those options.
Yeah, I tried it. Nothing worked. Okay, so can I try to leave and come back, maybe?
Sure.
Or
yeah,
Totally.
yeah.
Sorry.
We're not going to disappear.
While Laura is leaving and rejoining, there's one question in the chat that I was particularly curious about. Do distinct nans compare? Well, I guess they're all not equal. Does Python treat distinct nans differently?
Yeah, Mark, you thought you were done, but oh, you're muted. Let me.
Sorry, I lost the window. Sorry, the quick answer is Python mostly doesn't care about distinct nans. It doesn't expose payloads. It kind of exposes signs indirectly through copy sign and things. So people get surprised if, yeah, okay, I'll defer.
Hey, I'm back. Do you
Hi.
see it now?
Yes.
And now you see it going?
We just see the preview view with the
now?
full deck.
You see it going, like they are progressing?
We just see your last slide.
Nope.
Oh, Laura,
Okay.
full screen? Can you unfull screen the
Oh yeah. When you share your screen, I think you may have selected to share just one window.
Yes.
And if you choose to share the whole screen, it should be the first option called something like desktop 1.
Oh, let's try.
Then,
What about now?
there we go. There we
Yes.
go. That's perfect.
I'm so sorry.
I was just saying
Okay.
over the break, we haven't had too many technical difficulties. So
You jinxed
I
us,
it.
Pavel.
It's my fault.
You jinxed us.
All right. Please, Laura, go.
Yeah, so hi, I'm Laura and I work at the National Institute of Aerospace, and this is a work in this presentation. I'm gonna talk you about how to generate guard stable C floating point code from a real number specification. So we all know that writing floating point code is challenging, and this is because when we have a round of error, the result of our floating point computation can be unpredictable, and it can be very different from the ideal real number result that we have in mind. In particular, when these floating point errors affect the evaluation of a Boolean guard inside an if then else, for example, we also have that the control flow of the program diverges. And this problem is known in the literature as unstable guard or unstable test. So we have found several occurrences of this kind of errors in some safety critical avionics software that was developed both at NASA or other institutions. For example, in algorithm for determining the position of an aircraft, or resolving some detect and avoid conflict, or in the geoffensive of drones. And we know that in this particular application, it's very important to have a rigorous round of error handle or estimation. So our approach to this problem was that of trying to generate and verify in an automatic way a C implementation that uses floating point from a real number specification that is written in a high-level language like VBS, which also has some theorem prover support. And this floating point implementation should also be instrumented to detect when this unstable guard, so this divergence between real and floating point control flow happens. And also it should be annotated with information on how the round of errors are accumulating. So we decided to integrate 3 different formal methods tool to do this. One is our floating point analysis tool that's called PRECiSA. Then we have the interactive theorem prover PVS, and finally the static analysis suite from Abbasi for the language C. So this is a very high-level overview of our approach. We will have PRECiSA that takes in as input a real specification written in the language of PVS, and will automatically generate 2 things. One is a C implementation using floating point number of this specification, which is annotated with information on the floating point error. And the other is a set of certificates stating the correctness of these floating point assertions. Then we're going to use from Abbasi to analyze this C program and generate a set of verification conditions that will be discharged in an automatic way using PVS. So to give you an idea of how this toolchain works, we are going to have this very simple program, which is a real specification of an if-then else. And of course, if we decide to implement this using floating point numbers, in a naive way, so just replacing the operators with the floating point counterpart, we can see that the evaluation of xy greater or equal than z can be different in the real and in the floating point world. And in these cases, we may have a difference between the 2 programs that can be as large as 2. So for solving this issue, we have defined a program transformation or instrumentation called tau. So the idea behind it is very simple. What we want to do is to replace the original floating point guards with new guards that are more restrictive and takes into consideration the round of error that may occur in the evaluation. So we're going to, for example, replace this xy greater or equal than z with this new guard, which is xy minus z greater or equal than epsilon. And where epsilon is an over approximation of the round of error. And in this way, we're going to take the then branch here, only when this is also true. And symmetrically for the else branch, we're going to do the same. And for all the other cases, so when the arithmetic expression is between minus epsilon and plus epsilon, we're going to return a warning. So for these specific cases, it may happen that the original program, real and floating point control flow diverges. So we have shown that when the transform program returns a value that is not a warning, then the original program returns the same. Otherwise, every time we have a divergence, we're going to return a warning. And of course, because of the over approximation of epsilon, we may have false alarms. So the more precise epsilon is, the less number of false alarms we're going to get. So now that we have an instrumented version of our program, we can then generate the C code and also annotate it with information on the round of error. For this, we're going to use the ACSL language for annotation, which is the one that is used for from a C. So I'm going to show you the C transformation with this very simple example taken from the Daedalus library for detect and avoid. And this function TCOA computes the time to altitude of 2 aircraft. So the C code that we can generate with PRECiSA, it looks like this. So we have the main body of the function, floating point function, that is instrumented to return a warning when our guard is between E and minus E, where E is the error. And then we generate a set of annotation, and the most important is this one, which is the post condition that we want to ensure, which is every time the result is different from a warning, we don't have instability, so we don't have divergent paths. And additionally, we want to ensure that given some initial values for our argument, if the result is not a warning, then the difference between the result of our function and the initial real number specification is at most this number here, where this number is computed by PRECiSA. So now this program can be fed to FRAMAC. And FRAMAC, what it does is call the WP analysis, which is the weakest precondition analysis, and generate a set of verification conditions. So what we have done is customize this WP analysis to make the FRAMAC generate verification condition in the language of PVS that can also use the same PVS certificate that we generate from PRECiSA. And in this way, we can take this certificate that certifies that our the round of error estimation that we have done is correct. And this verification condition that ensures us that we don't have unstable test. And we can prove it now with PVS. So here it's important to notice that normally, PVS is in an interactive theorem prover, so you have to do your proof by hand. But for these cases, we have defined automatic strategies in order to discharge this condition and certificate in an automatic way. So to finish up, we have, in this work, we have integrated 3 different formal methods tool in order to generate a C code from a PVS real number specification. And also we have integrated FRAMAC with PVS in order to automatically verify C code that contain information on the round of error in their specification, in their pre and post conditions. So you can find our implementation in the NASA GitHub. It's open source. And we have applied this method to some fragment of NASA formalization of Polycarp, which is a library for geofencing, and Daedalus, which is a library for conflict detect and avoid. So thank you for your attention.
So I'm gonna try to keep ourselves roughly on schedule by cutting off questions early here. But yeah. I do want to say there's a lot of questions in the Slack. And so this is kind of another good thing about that. So if you could, you can answer the questions there. And I'm going to try to move us along to the next talk. Yeah, Zach?
That's okay. Sorry for the inconvenience.
No, sorry, it didn't work. Okay, so our next talk is going to be from Rosa Abbasi. She's a PhD student working with Eva Drulova at the Max Planck Institute in Germany, and she's working on scaling the verification of floating point properties. So that's what this is going to be about. So Rosa, please. You are muted. Hold on.
Thank you. Can you see my slides?
Yes, we can see your slides and we can hear you.
Okay. So, hello everyone. I'm Rosa Abbasi from Max Planck Institute of Software Systems, and today I'm going to talk about deductive verification of floating point Java programs. This is a joint work with Karlsruhe Institute of Technology and Chalmers University. So, without further ado, let's see why we think this is an interesting problem. Somehow I cannot go to, okay. As you may know, one of the main challenges of floating point arithmetic for non-experts is its unintuitive behavior and the special values that the IEEE 754 standard introduces. For example, dividing 0 by 0 over doubles results in not a number and doesn't produce an exception. And rules such as associativity and identity may not hold. So for most applications, these special values and their absence is a prerequisite for further reasoning about the correctness of a program. But when we have a real object-oriented code such as this one, then it's not easy to say if these special values occur anywhere in it. This is a class representing an RL circuit and contains methods to compute the instantaneous current of the circuit. So we think that automated support for writing correct floating point programs is necessary. And reasoning about real-world object-oriented code such as this one then requires also support for features such as heap and combining different analysis with floating point reasoning. Key is a deductive verifier for Java programs, and it supports object-oriented design. Key already has the infrastructure for supporting object-oriented programs, so we just needed to add support for floating point numbers to it. So first, let me show you the key workflow, and then I'm going to talk about how we extended it. For input, we have a Java program that's annotated with Java modeling language or JML. The classes can be specified with class invariants that the program has to maintain at critical points, and methods are specified with method contracts, consisting of pre and post conditions, with the understanding that if the precondition holds before the method is called, then the post condition has to hold after the method is returned. Then the program is loaded into Key, and Key automatically generates verification conditions. Key uses rule-based symbolic execution and generates first-order formulas that are called proof obligations or goals. The language for a specification of induction rules is called the tacklet language, and the rules are called tacklets. The proof obligations are then discharged either directly by the verifier itself or discharged using external tools such as SMT solvers. To extend Key for supporting floating point programs, the basic approach is the same as before. For discharging proof obligations, there were two main ways to consider. One is to create a floating point theory inside Key. So by adding axioms and deduction rules, then the desired properties can be proven by Key itself. The other option is to take advantage of the strong support in SMT solvers for floating point theory and discharge and translate the proof obligations to SMT-lib and call external solvers. For this work, we took the second option, but what will happen when there is no SMT-lib equivalent for a function? So when we have complex functions such as transcendentals in a program, then there is no SMT-lib equivalent. For these cases, we introduced an approximate axiomatic approach. And by these extensions, we closed the gap for a verification system with close to full coverage of sequential Java. Our work is inside the Key verifier, but we expect our approach to be portable to other verifiers as well. So we made several extensions to Key. Other than the basic extension of Key's type system, lexer, and parser, we introduced functions and predicate symbols to formalize operations and comparison over floating point expressions. This example here shows a JML specification that makes use of FP_NaN and FP_infinite predicates, which state that a floating point expression is NaN or infinity, respectively. We also have another predicate called FP_nice, which states that an expression is neither NaN nor infinity. Our second extension is adding tacklet rules for translating floating point expressions from Java and JML into first order formulas. So for example, this program here is translated to this sequent, which is a first order formula by applying this rule among other ones. And then our third extension is a modular translator that translates these first order formulas or proof obligations into the SMT-lib format, and it supports the previous features of KISS translator. So it supports heap and integer arithmetic, and now also has support for floating points. So with these extensions, now let's see what sort of properties we can prove. We can prove two classes of properties. The first one is the absence of special values. So by using FP_nan, FP_infinite, and FP_nice predicates. The second one is that we can specify functional properties that are expressible in floating point arithmetic. For this example here, we check that the difference between an original vector and the one that's rotated 4 times by 90 degrees is less than e to the minus 15. So for when there is no SMT equivalent for a function, the previous approach won't work. But we observed that we don't always need the exact reasoning about transcendental functions, and using a sound axiomatic approximate approach is sufficient and efficient to prove some properties. So first, let's see what our axioms look like. The axioms are expressed as quantified floating formulas and capture high-level properties of library functions. They comply with the IEEE 754 standard. And in particular, they encode properties regarding value ranges, and I want to show that a function application is not null. The example here shows an axiom for the cosine function. The axiom states that if the input argument of cosine is neither none nor infinity, then the output of cosine is between -1 and 1. So clearly, since we don't have the actual implementation of functions, then we are not able to prove arbitrary properties, but we can still, these axioms are sufficient to be able to prove the absence of special values. For example, we are able to prove the return value of this function is neither none or infinity by using the axioms that I mentioned above. So we saw that with the flexibility of deductive verification and key, we can instantiate our axiomatic approach in 2 different ways. We encode transcendental functions as uninterpreted functions and either axiomatize them in SMT queries, or alternatively, we encode these axioms in key as Tacklet rules. So with the first approach, function definitions and axioms are added to the SMT translations. This is the same axiom as I mentioned before in the SMT format. And with this approach, axioms that contain quantified floating point formulas are added to SMT translations. We observed that in our experiments that SMT solvers struggle with quantifiers in combinations with floating points. So for our second approach, the axioms are not encoded as SMT queries, but instead are encoded as Tacklet rules in key. So this is the example of the previous axiom as a Tacklet rule. And then the rules can be applied automatically or manually by user. Manually here means that the user can select which rule to apply, but the rule application itself is automated. So after the necessary tacklets are applied, then the proof obligations are given to the SMT solvers for final solving as before. And since in this approach, quantified formulas are instantiated by applying the rules, then we won't have quantified formulas in our SMT translations later. For our evaluation, we gathered existing floating point Java programs from the web that represent real-world applications. Each one consists of methods and is composed of arithmetic operations and method calls to potentially other classes. So the benchmarks are loaded into key, and then key closes a non-floating point goals, and it generates proof obligations really fast, and it takes less than 9 seconds to generate the proof obligations for our benchmarks. And then the floating point goals are discharged using SMT solvers. Here we can see the performance of 3 solvers on discharging the remaining floating point related open goals for our benchmarks with valid contracts. To summarize the results, CVC4 has the best average running time and MathStat has the most number of goals that it can validate. In our another experiment, we compared the 2 axiomatic approaches that we introduced for programs containing transcendental functions, and we observed that having axioms encoded as taglet rules improves the performance. So Z3 can prove more goals and CVC4 can prove all valid goals. This improved performance is the result of avoiding floating point quantified formulas in SMT-lib translations. To summarize, we presented the first floating point support in a deductive verifier for Java programs by combining keys building deductive reasoning with reasoning of SMT solvers. We also introduced an axiomatic approach for programs with transcendental functions by combining rule-based deduction and SAT-based SMT. You can find the details of our work in this Taka's paper, and thank you for your attention.
Very nice work. Yeah, this is exciting to see the ability to lift this to sort of, real user level code. One thing I wanted to mention, if folks also want to raise their hand in Zoom, we can do questions additionally that way. There was a question from, actually, Martin, please go ahead.
Not a question, just a comment, lol. Great work, really exciting. It's brilliant to see our stuff used. Let me know if you have problems with CVC4.
Thank you.
Yeah, the CVC4 performance was really impressive. I think my mental model of SMT support for floating point is a little bit out of date. Chandra also had a question. I'm not sure if you want to ask that live.
Yeah, hi Rosa. So my question was, so is there ever a problem of encoding transcendentals as uninterpreted functions, or is there any drawback, or does it always just work, or do you lose anything by doing that?
So we cannot always prove every property. That's the drawback. So we are dependent on our axioms. If we overdo it with axioms, we can prove properties, but then we have to add all of these axioms to key. But that's the drawback. So
got it.
Yeah.
Cool, thanks.
Welcome.
And I think with that, we'll go ahead and move on to the next talk. But there's, obviously, if folks have additional questions, please continue the discussion in Slack. I'll hand it back over to Pavel.
Yeah, thank you. Yeah, very exciting work. So our last talk in this session is by Brett Saiki. Brett's an undergrad at the University of Washington. He's advised by me and Zach. So as an undergrad, his very first talk ever was last month at ARITH, on the same work. And broadly, he's been working on a lot of FP bench development as well. So not just the Harvey stuff he'll be talking about, but he's also done a lot of work on the compilers and testing for FP bench. So he's been really instrumental in a lot of this. And quick advertisement, Brett is interested in internships for next summer. So if you have something to talk to him about, do get in touch with him on Slack. And Brett, with that, let me hand it off to you.
Thanks, Pavel. One sec. All right, you can see my screen. Cool. All right, hi, I'm Brett Saiki, and today I'll be presenting our work on combining precision tuning and rewriting. So when writing numerical code, there are 2 things we try to minimize: error and latency. In certain scenarios, you want to minimize latency over error. In others, error over latency. And of course, there are other situations where we want something in between. So for any expression or function, we have a Pareto frontier of possible implementations. And the key thing is, no one trade-off is right for every application. So we have to search the Pareto frontier depending on our needs. And we generally use 2 techniques for this: precision tuning and rewriting. Now, in general, precision tuning increases speed by lowering the bit width of the representation, while rewriting increases accuracy by avoiding things like cancellation. Now, for both of these techniques, it's hard to know where to apply them. And in recent years, there have been numerous tools that automatically use precision tuning or rewriting. Now, if you have an expression and you're just looking at it, it's hard to know which technique you should choose. And maybe you want to use both. So in the past, you take a precision tuning tool, take a rewriting tool, and use them together in some fashion. This raises some key issues. What order should you use these tools in? How many times should you run them? And of course, it's difficult to share data between runs. And so the obvious fix is to use precision tuning and rewriting within the same tool. And what we found is combining these two techniques simultaneously produces a rich set of Pareto optimal accuracy versus speed trade-offs. In addition, we found that finer grain interleavings of the two techniques create better Pareto frontiers. Precision tuning is really just a rewriting problem, and local error analysis helps guide both of these techniques. So we took these key points and we made a new tool called Pareto-Herbie, or Furby for short, that takes an input expression, automatically applies precision tuning and rewriting, and produces a set of implementations that are Pareto optimal. So before I talk about Furby, I'm going to talk about the tool it was built from, Herbie, so we understand some key concepts. Herbie is a rewriting only tool that improves the accuracy of floating point expressions. In a nutshell, it takes an input expression P, points in its input domain for evaluation, generates candidates in this improved loop, and then produces an output expression P prime through something called regimes. Now, a little bit more in depth on these phases. Localize takes an expression from the candidate table and identifies which operators have high error through something called local error analysis. Now, what this does is for every operator, you take the exact value of the children, you compute the approximate and exact results at that operator, and you compare them. And this should give you a good idea of which operators are problematic. In addition, this prevents the error of the children from affecting the error of the parent. Now, once Herbie knows which operators are bad, it uses a database of hundreds of rewrite rules to find and replace sub-expressions to produce new candidates. There's some additional phases I won't mention. And lastly, there's this prune phase that makes sure to only add the candidates of interest to the table. Now, once the improved loop has been run multiple times, Herbie extracts an expression through something called regimes, which essentially combines candidates. Here's a good example. Let's say you have a candidate in the table with this error profile in red and another candidate with this error profile in purple. Regimes will combine these two candidates with a branch condition to create a new expression that is more accurate than any of the two candidates on their own. So that's Herbie at a really high level. And we can think of Furby as an extension of Herbie with precision tuning, as well as producing multiple output expressions. And so we made these key changes here highlighted in blue. And the first one I'm going to talk about is rewriting. So here is an example of rewrite within Herbie. It's a distributive law. And the key is Herbie uses a single global precision. So if the user specifies double, all these operators produce double precision results. But we want multi-precision expressions in Furby. So the key is we make the operators precision specific. And this allows us to match on an expression by both the operator and the type. Now, this allows us to introduce a new class of rewrites called precision rewrites that can change the precision of an expression. And these two classes of rewrites implement rewriting and precision tuning within Furby. Now, there's this question of where should we apply these new rewrites? Just as Herbie rewrites at places of high local error to improve accuracy, Furby increases precision at places of high local error to improve accuracy, and decreases precision at places of low local error to improve speed. The next phase we changed was pruning. Once again, pruning takes those candidates that were generated within the improved loop and throws out the ones that are considered non-optimal based on some criteria. To make it into the table in Herbie, a candidate must be more accurate than every other expression on at least one sample point. This really won't work in Furby because the table will become biased towards slow but accurate expressions. So things like 1 or 2 term polynomials generally won't make it into the table. And the fix is to only compare against other expressions that are at or below the cost of the candidate. In other words, it makes it into the table if it is best on class on at least 1 point. But what is cost? It's really just a measure of an expression's latency. And what we found is it's really hard to get precise timing data for each candidate, or rather it'd be impractical because we'd have to evaluate the expression many times. And within a single iteration, Furby may produce thousands of candidates. And we really only need a relative speed comparison between candidates. So we should just use a cost model to quickly estimate the latency of these expressions. Here is Furby's default cost model. It's quite naive, but I think it paints a good picture of what a cost model might be. For every operator, we assign it a cost. Arithmetic operators get something low, while library functions get something high. And we multiply the operator cost by the bit width of the representation. An add-in double is twice as expensive as an add-in single. And to calculate the cost of an expression, we just go through the AST and add all the operator costs, with the exception of conditionals. And so in general, of course, better cost models exist. The one I just presented was quite naive. And the key is Furby is modular. So a user can swap out their cost model for the default one. Yeah, so that's pretty. The last phase that was changed was regimes. Herbie's regimes algorithm only produces a single expression, but for Furby, we can actually just iteratively run it on the candidate table to extract multiple expressions. So at a high level, we have a cost bound that is initially higher than any of the costs in the table. And then we run Herbie's regimes algorithm on the subset that is cheaper than this cost bound. So in the first iteration, that's all candidates. And we extract an expression. Then we decrease the cost bound. So we're guaranteed a different expression in the next iteration. And we repeat until no candidate in the table is below this cost bound. So here's a more concrete example. Imagine we have this input expression up in the top right, and we've run the improve loop multiple times. So now the table is full of candidates. We step through extracting expressions through regimes and lowering the cost bound. And as you can see throughout this process, by mapping the error latency of the candidates, we extract a proto-frontier of implementations. So that's regimes. For the evaluation, we use two benchmark suites. The first is numerical methods for scientists and engineers. This is a standard textbook on numerical analysis, full of kind of naive, high error examples. And the second is physically based rendering, which is an open source textbook describing how to render photorealistic scenes. So here are three examples. The black square in the bottom right is the cost and error of the input expression, while all the red dots are the cost and error of the output expressions from Furby. And the key here is if you just ran Herbie, you would have only found the expression down there in the bottom right, because all Herbie cares about is accuracy. But Furby finds all these other interesting implementations, especially this one in the bottom left that only uses arithmetic operators. Here's a second example. Once again, Herbie finds that one in the bottom right, but there are some that are much cheaper for very little accuracy loss. And then here's a third example. And I think the interesting thing here is Furby finds these candidates that have lower cost and lower error than the input expression. I made the claim in the beginning that finer interleavings of the two techniques create better proto-frontiers. And so we used 7 treatments on the 2 benchmark suites. The 4 of interest are the 2 in the middle that chain the 2 techniques back to back, and the 2 on the right that interleave the 2 techniques within the same tool. One of them is Furby, but the other is like a coarser grained, kind of less efficient variant of Furby. And here's the aggregate result from the 2 benchmarks. What these curves answer is, imagine you select a single output expression from each benchmark within the suite, and you sum the costs and sum the errors. For a minimum cost bound, for a cost bound, what is the minimum cumulative error you can achieve? And for both of these benchmarks, the 2 treatments that interleave precision tuning and rewriting produce the best proto-frontiers, or aggregate proto-frontiers, while the 2 treatments that chain the 2 techniques together don't produce as high quality proto-frontiers. So that's the evaluation. Here's the rest of the team that worked on the arith paper. So I'd like to thank them. And that's the end of my talk. Furby is currently in experimental mode within Herbie 1.5, which actually just released last week. So please visit our website for more information. And thanks for listening.
Many thanks, Brett, for the great talk. And if anybody has questions, please feel free to raise your hand. We got a couple here in the Slack. Ignacio, I'm not sure, would you like to ask your question live or?
Sure. Can you hear me?
Yeah.
Yeah. Where does the rewriting happen? Is it in the front end, middle end, or back end?
Okay, so this diagram in the second diagram shows where the rewriting happens. There's I guess it's the middle is the answer.
Okay.
In the improve loop. it takes an expression and then just applies a bunch of rewrite rules to produce many candidates.
I see. And then you compile this with a given compiler and run it, or?
No, actually, it's all, we don't actually run it with a compiler.
Oh, okay. I see.
Yeah.
Okay. Never mind then. All right.
But you could.
Yeah.
Oh, you could do that? Okay.
Yeah, I mean, in that case, it's sort of a pre-processing.
It's a pre-processing, and then optimizations may totally destroy the rewriting, right?
As long as you don't have fast math on, they're not supposed to, but compiler writers are cowboys sometimes, so who knows?
Right, all right.
And I think Jesse also had a question about local error.
Okay, thanks.
So Zach, I think Jesse isn't here, so you're gonna have to proxy his question.
I think Jesse's. I think the audio is just connecting. Or
sorry.
Okay.
Yeah. I guess I was just curious about the cost function that you used. I know there's work on, for example, looking at the derivatives. There's this like adapt paper, for example, that has this sensitivity analysis. So I just wanted to hear a little bit more about sort of cost functions that you were exploring.
Yeah. So one of the critiques we got on the original RIF paper was the fact that we didn't use common subexpression elimination. So I did run that recently. It definitely changes the output slightly. Like the curves, the aggregate curves definitely move to the left because everything becomes cheaper. Because generally the more expensive candidates have common subexpressions. But other than that, I haven't really experimented with that. We have some ideas on synthesizing cost models. Like you can imagine you have something in Herbie that runs a bunch of benchmarks to identify, like on your system, what's the latency of certain operators. So yeah.
And Santosh also had a question about the cost function, maybe in comparison to compilers. Santosh, I don't know if you want to expand on that or.
So my question is more about like how accurate do the cost models need to be? Like for example, compiler cost models have been tuned for years, right? And that's why they get the best possible performance. And so one naive cost model that you could use is like, oh, FP16 is like my better performance than FP32, great better than performance than FP64. Like, will a first order cost model work, or like, what is the sensitivity to the accuracy or fidelity of your cost model to the target architecture?
Yeah, it's hard to say. I really have to do like more testing with cost models to answer this. You can kind of think of Furby as like purely parameterized by the cost model. So, I mean, it kind of just outputs whatever based on it. So if you had something really accurate, I guess it would produce really good implementations. Yeah, I don't really know how to answer that.
I think one thing too is that you just need the relative ordering. So because we're not using it for prediction, it's the way in which the cost function would break Furby is if it was so wrong that it changed the Pareto frontier. As long as the relative ordering is right, you'll still get the same frontier. It's just that the cost numbers themselves don't mean anything. So that sort of provides some wiggle room, some flexibility on the cost model to keep it cheap. But yeah. Great, well, thanks. And we're pretty good on time so far. So, and if there's any more questions about Furby, you know, Brett's in the Slack, please hit us up. But I think I'll turn it over back to Pavel.
Yeah, okay, so thank you all of our speakers so far. So this is the end of our second session. So we're gonna do about a half-hour break so that people can, you know, do whatever they need to do, stretch their legs, grab something to eat. And then we'll be back here in about a half hour. And the first talk of session 3, I believe, is Alison Baker's talk on correctness and validation for climate models. So very excited for that. Definitely don't want to miss it. See you all in a half hour. Zach, if you unshare, I can share my my version of this, which has little faces in it.